Okay, the last time we met, we discussed acid-base chemistry and neutralization reactions. So the first thing I would like to do is kind of bring us back into that conversation again. And what I've done is I've inserted a slide that was not previously in your notes. And so let's take a look at this together and how we would go through this particular problem and answer the three questions that are listed on the slide. So we have a statement that equimolar solutions of hydrofluoric acid and potassium hydroxide are mixed. And we want to find, one, the molecular equation and balance it, two, the total ionic equation, three, the net ionic equation. Then, of course, we want to be able to depict this as a molecular cartoon. And finally, we want to classify the reaction. So let's take care of these one at a time. And this is going to really be able to allow me to test your mastery of a lot of different things at once. So I'm going to start with the molecular equation. Hydrofluoric acid is HF. It is soluble in water, so we want to give it a subscript AQ for an aqueous ion. That simply means it is soluble in water. KOH is potassium hydroxide. Also very soluble in water. As with any type of acid-base reaction, we are going to obtain water, H2O. Now this water will be a liquid, hence the the subscript L. And also we will get the relevant salt, potassium fluoride. And potassium fluoride. Remember, all alkali metal cations and their corresponding salts will be soluble. So this gives us the molecular equation, and of course it is all one-to-one stoichiometry, so it is already balanced. Now, for the total ionic equation, it is very important to realize that HF is a weak acid. And as a weak acid, very little of HF is going to dissociate. So HF will not break up into ions. So we'll have HF, AQ, plus, now the KOH will break up, K plus, AQ, plus OH minus AQ, will yield H2O. Again, H2O will not significantly ionize. So in the context of how we depict this on paper, we will show it as though it does not ionize. And of course, KF does dissociate, so we will write it as K plus and F minus. Again, this is the total ionic equation, and it is properly balanced. Now, in order to go from the total ionic equation to the net ionic equation, one must discount chemical environments that simply do not change. Notice that I have K plus as a reactant, and I have K plus as a product. In both instances, K plus is surrounded by water molecules. So it absolutely does not change during the course of the chemical reaction. What we're left with at that point is going to be our net ionic equation. So we have HF aqueous plus OH minus aqueous yields H2O liquid plus F minus aqueous. Notice the number and types of atoms are balanced. Notice the charge is also balanced. We had a -1 charge in reactants. We have a -1 charge in products. So now, the net ionic equation, which really tells us exactly what is changing in this reaction, is neatly summed up and boxed in orange. Next, we want to be able to look at the net ionic equation. So what we really want to be able to do is to look at a set of beakers in which we have our reactants, and then we have a third beaker into which we've poured each of our two reactants. To properly depict this, I am going to use a program called ChemDoodle. ChemDoodle is a chemistry drawing program that you can try for free for 30 days. I like it quite a bit because it allows one to draw glassware that you might put into a lab report, balance chemical equations. As you get into more sophisticated structures that you might encounter in Gen Chem 2 or organic, it just is a really nice way of depicting things. So I'm just going to copy these and try to build 3 of them. Well, it doesn't look like it's going to let me copy and paste this, so I'll tell you what. We'll just go back to old-fashioned drawing. So we'll have a beaker with HF. And we can choose to depict this numerous ways. What I'm going to choose to do is to emphasize the fact that very little of this is dissociated. So hydrogen will be black and fluorine will be green. And I'm just going to draw a few of these. And what you can do with this it's a weak acid, which means very little of it ionizes, but there's always going to be some amount that does ionize. So I'm going to draw one of them being split apart and of course solvated by water, which cartoonishly I'm going to depict as this blue circle. Those are water molecules that are surrounding the anion and the cation. So that's beaker 1. In beaker 2, I'm going to have the strong base, KOH. That is completely ionized, or very nearly so. And of course, all these are going to be surrounded by water, which is what I'm attempting to render here, is that they're all solvated by water. And then finally, we can look at the product. In our third beaker, we've made the water molecule. So in our second one, if we were to draw a little key, orange is K+, and lavender is OH-. Green is F-. Black is H+. So I'm going to make several water molecules, and they will not be solvated. So this is really the change in the reaction. Instead of black either being bonded to green or surrounded by water, it's now bonded to lavender. Now, the orange is not going to change. It was surrounded by water before, it's going to be surrounded by water after. And so in my cartoon, what becomes really important is that this environment is not any different. It is a spectator ion. And of course, I'm also going to have water surrounding F-. Now, you don't really have to worry about how many of the green ones that you draw, since this is weak. And to be real honest, you should have a substantial number of them that are still bonded to hydrogens. And then this is a really good molecular depiction of the reaction of HF with KOH. There's still a substantial number of HF molecules that do not ionize. This is what you want to do on paper to properly depict what is happening in this reaction. Last question. We want to be able to answer what kind of reaction we have. And there's a few ways that we can do this. We can say it is double displacement. We could say it is neutralization. More specifically, we can say it's a weak acid, strong base. Neutralization. So this is the complete depiction of this particular problem. This is something I will expect you to be able to do on take-home tests, also on in-class quizzes and in-class problem sets. I will have a problem set that should be posted before class time tomorrow night. But this just gives you an idea how we want to go through that process to rationalize all of these answers. So practice on a couple of others. In fact, let me give you a couple to work on, to consider. So number one, aqueous solutions of silver nitrate and lead 2 chloride. Actually, let's make that lead 2 hydroxide. Are mixed. So again, I want the molecular equation balanced. I want the total ionic equation balanced. I want the net ionic equation balanced. I want a molecular cartoon. And I want you to completely classify the reaction. And number 2, equal molar solutions of hydrochloric acid and ammonium hydroxide are mixed. Answer the same questions for both of these. During office hours, via emails, be happy to answer these questions or to give you guidance as to how we actually solve them and go through all of the steps, but I would like you to take a stab at it first.